When it comes to circular motion, practice makes perfect. Let's do some practice questions. One I want to do is to figure out the acceleration of the end of a second hand on a clock. And I'm talking about one of those clocks you see in a swimming pool, or above a swimming pool, where the second hand moves smoothly around at a constant speed. Let's pretend there's a dot on the very end of that second hand, and we're going to figure out the acceleration of that second hand. Actually, we'll make it a really big clock with a second hand that's moving smoothly. So using my elliptical tool here, that is the face of the clock. And this is the second hand pointing directly up. I want the center of the circle. There. Pretend there is a red dot on the end here. If that red dot is moving in a circle at a constant speed, as you would expect it to, it will experience some acceleration. Let's figure out that acceleration. First of all, some details. This clock, it's very large, has a total diameter of 10 meters. It's more like a clock tower. But again, the goal is to find that centripetal acceleration of the red dot there. It's the second hand. So the period is going to be the amount of time it takes for the second hand to make one trip around the circle. T is equal to 60. If we know T, and we can figure out R, if we're clever, the radius is half of the diameter, so the R is 5, then we can use this formula up here to find the centripetal acceleration. Let's give that a go. AC is equal to 4 pi squared times 5 over 60 squared. Is that right? Does it take 60 seconds for the second hand to go around? I think so. And that comes to 4 pi squared times 5 divided by 60 squared. Calculator says 0.055. Actually, 0.05, we'll say 0.0548. That's the better approximation. And since it is acceleration, that's meters per second squared. Why is that so low? Well, first of all, the second hand moves quite slowly around the clock. And secondly, the clock is quite large. So if speed is low and the radius is big, you expect this value over here to drop. Or, alternatively over here, if R is big, well, that's a bit funny. If R is big, but T is also big, since this is going up by a square and this is going up by power of 1, you would expect that overall to drop. That's interesting. So R, just because R is big, doesn't... I like my second explanation better. If T is big, if the period is big, even if R is big, since that's squared, this is going to go down faster than that can push it up. Moving on to the next question. A playground with a child on one of those spinning platforms. Get rid of all that nonsense. There's the spinning platform with the central point there, and it's just going around like that, being pushed by some friendly older brother. The child has mass 45 kilograms. The platform has total diameter 2 meters. And the child, the older brother sees, because he's standing here pushing, goes around every 1.7 seconds. The child whizzes past him. This isn't a very strong child. The child who's on the rim of this platform has a maximum grip strength of 450 newtons. That's the max strength with which they can grip the bar of this platform. Let's figure out if with that max strength they can hold on to this platform. Because we all know what happens if you're not strong enough to hold on to these things, or if your older brother pushes it around too fast, you go flying off like that. Land on the tan bark. Okay. The centripetal force required to keep that child moving in that circle is given by that formula there, 4 pi squared. We know r is 1 meter, it's half of 2, which is the diameter, multiplied by m, that's 45, divided by t squared, 1.7 squared. Don't forget that square. I used to always leave it off and it would totally skew my further answers in the question. So plugging this into the calculator, I have a centripetal force of 614 newtons. That means that the force of the ride of the platform's bars on the child has to be 614 newtons. So you can imagine a pole there with a hand wrapped around it, like so. The force of that bar on that hand to keep the child on that ride is 614 newtons. And that also tells us that the force of the hand on the bar would have to be 614 newtons. But since the child has a max ability to hold on of 450 newtons, the child does not have the necessary force to hold on to this ride. So at this moment in time, even though they're still on it, they are about to fall off onto the tan bark like